Great. Well, thank you everybody for sticking around to the end. I'm super excited to be here. My name is Emma Brunskill, and I'm Assistant Professor of Computer Science here at Stanford. And I'm really thrilled actually to get to go at the end because I feel like the work I'm going to talk about is going to build naturally on some of the conversations we've been having about efficacy, about big data, and about thinking about the future of work. So feel free to interrupt me at any time. I'm happy for this to be pretty informal. This is near the end of the day. So I found this statistic from the Bureau of Labor Statistics pretty interesting. This is saying that for at least some classes of individuals, they're changing jobs around every 3 years. Now, in the Silicon Valley, it's probably more than this. And I think for many people that are going to be entering the workforce, it's likely going to be more than this. And what does this mean in practice? It means that people are going to be sort of continually retraining. We're not going to have this notion of K through 12 or K through 16, but we're going to have this notion of really finally embodying lifelong learning. And in order to do this well, it means we're going to need to have really good, effective tutoring systems and educational support. So a lot of my work, I'm really a machine learning person. I'm a machine learning person that cares about applications that might help people. And so the work that I do, some of you might be familiar with computer vision, where we think about how do we teach computers to see. I think about how do we teach computers that learn to help us. And in particular, a lot of the applications I think about when I think about helping us is in terms of education and somewhat in healthcare. So I think that a lot of the intelligent tutoring systems we've seen can really be phenomenal. Some of the results when I first started hearing about this, of some of the work that's come out of the military, some of the work that we've seen from Carnegie Mellon, where I used to be faculty, where we can see things like we're doubling learning outcomes in the same amount of time, or we're drastically reducing the amount of time people need to become proficient, is absolutely phenomenal. The problem is these typically require enormous amounts of resources. They require enormous amounts of money, they require enormous amounts of expertise, and often both. And not just that, but they often require years of study, which as we've been hearing, in these sort of fast-paced moving environments, if it takes us 4 years to create a system, the economy is changing, the skills people need are changing, and that new thing that we've just created may already be outdated. So I think a lot about sort of how would we democratize this, and what do I mean by democratize? I mean there are all sorts of skills that we learn, sometimes by YouTube, sometimes by our friends, where we'd really like to have more support. So I think about this a lot. I'm a parent. I've read lots of parenting books. They tell me how to be a perfect parent, and I'm like, okay, great. How do I do this today with my toddler that is currently screaming about, not getting a brownie? And the problem is it doesn't provide me with a curriculum, it provides me with information. And unfortunately, I'm not the best at processing information. I really need curriculums. Now, I don't think I'm alone. I think a lot of us need curriculums. We need ways to go from information into habits, into internal knowledge. And a lot of these types of skills we'd like to internalize, we don't have $10 million to run a study about it or even to develop it. So how could we take some of the really incredible outcomes for intelligent tutoring systems and be able to embed them into all sorts of systems we might want to create, even for training just 10 people, or training all parents, or looking for all sorts of these different types of interactions. So there's a number of different ways we might imagine doing this, and when I say scale here, I'm meaning scale a little bit differently than the sorts of scaling that Zach is talking about, where we're thinking about how do we scale up to millions and millions of users and huge numbers of courses. I'm more thinking about how do we scale to lots and lots of different educational environments. And how could we do this when we're not going to have a lot of resources for any single one of them, but where it matters, where we would really like to sort of improve outcomes in those cases or reduce the amount of time it takes people to learn. So a couple different ideas you might think of is, okay, well, how do we scale these sort of intelligent tutoring systems? Maybe we could use authoring tools, or maybe we could build on some of these really cool platforms like edX that is trying to provide support for instructors to provide more adaptivity. I would argue these are not sufficient yet. One challenge with things like authoring tools is that they often rely on the instructors to create some sort of specialized content, and they often don't provide a lot of adaptivity for students at a meta level in terms of selecting educational content. Other things like platforms, things like OpenEdX and their A/B tests, typically rely on data. So they're going to provide us information about what might be effective, and maybe we can leverage some of this to try to provide adaptivity, but it's going to require us to have a sufficient user base to figure out what to do. And so what I'm going to talk about today is sort of the cold start problem. How do we start to provide effective educational adaptive material when it's in a small domain, maybe never we expect to get millions of users, so we have no prior data, and we don't want to require on having an expert instructor in order to provide adaptive curriculum. So in particular, we were thinking about this problem. I think a lot about sort of personalized adaptivity. I think about machine learning. But we're thinking about this case of how do we sort of start from no data and create an adaptive algorithm for sequencing problems that can teach students, given no prior data, better than an expert. So I want to be able to create systems that are good from day one. I don't want them only to be good after we have 1 million users. And this is actually a pretty hard baseline. People, particularly experts, are pretty good. So how can we do something that by leveraging adaptivity might actually be better than experts? And what is better going to mean? And this is going to go back to how do we define efficacy or even engagement? How do we define the types of metrics we would like these systems to do well in? So let's imagine that we're in this setting. This is a game called Catchy. It was developed by my colleagues over at Cornell, Eric Anderson's group, and it's for teaching basic vocabulary and ideas and grammar in Korean language learning. So let's imagine that we have this particular tutoring system, and we have a set of tagged pedagogical material. So some of this pedagogical material we could probably represent at different levels of abstraction. We could do things like saying this is something about color and shape, or we could say this is specifically about red triangles. Or we could say this is about shape and shape, or a particular circle and a triangle. So generally, we can always think about things at multiple levels of abstraction. We can think about subtopics versus is this part of computer science? Now, once we have this, can we try to provide an adaptive pathway through this type of material when we don't have any prior data? And in particular, does it help over a baseline? So the approach we're going to take is to say if you have this material and it's tagged with some features, and I think increasingly in, at least from sort of machine learning techniques, we may have ways to tag things, or we may have ways to generate tags from other forms of curriculum. Can we automatically organize this and then guide someone through it? So let's first of all think about just relating ideas by their features. Relating items by their features. So imagine if we think about having a particular item, like showing someone 2 red triangles and 2 green circles. And I guess what I should have specified here is what does the student have to do? In this case, the student has to figure out which of these characters corresponds to 2 red triangles and 2 green circles, and put them in these boxes in the right order to indicate that they understand what the vocabulary is and how it relates to the concept that is being shown. So these different forms of items involve different types of features, and we can imagine creating a graph automatically by which features are present in which items. So this sort of automatically provides sort of a hierarchy over material. Some material might only involve one idea, like green. Others might involve sort of combining different ideas, much as like what we do in language. And this sort of way of creating a graph was previously introduced by our collaborators, Eric Anderson, who showed that not only you could do this, but you could actually automatically provide some of this curriculum. So the key idea for how we can automatically do this ordering is that we just have to have essentially some way to relate the similarity of different types of items. And if some things strictly have more additional features or properties, then we're going to consider them to be harder. All right, so that's the first idea. The second idea is that there's some recent nice work that came out of France, which was talking about if you have such a graph, and in that case they assume the expert gave it to you, but let's imagine that now we're using this automatically constructed graph. If you have such a graph, how could you lead someone through it? And from here we're going to leverage the idea of zone of proximal development, meaning that we think of the learner as having sort of a frontier of what they have learned or not learned. So let's imagine that we have sort of these green nodes here, which are the items that or concepts we think the student has learned. We have these other blue items, which are kind of on that frontier of knowledge. And then we have other red items that we think students are not yet ready for. So that means we can look at how the student is doing, and over time we can grow that sort of frontier. And as they progress, we keep track of what they know or don't know. Now, this is similar to some other forms of statistical modeling for students. One of the key ideas here is that we're going to use very few, what I'm going to call hyperparameters. Essentially, there's very few number of free parameters for us to tune. One of my pet peeves is hyperparameters. We see those a lot in deep neural networks right now, which are very popularly used in machine learning. And it always makes you wonder about whether it's really the new algorithm or if it really is just tuning these parameters. It's also really hard to set these without data. So what are the parameters in this case? Essentially, we're keeping track of, are people making progress? And I thought this is a really nice idea from Benjamin Clement and others, which essentially is, we're looking at, over a particular time window, is their performance on the first half of the window different than the performance on the second half? If it's flat and good, they've probably mastered it. If it's flat and bad, they're probably not ready for it yet. And if it's positive, that means they seem to be improving. So we only need two parameters here because we're only looking at sort of history length and also some threshold to decide whether or not they've actually learned the material yet. Now, the other thing that we additionally wanted to consider in terms of adaptively selecting materials is forgetting. We know that spaced repetition is very helpful. I'm always curious that we see much less of that in STEM fields than we do in language learning. But particularly in this case, because we're focused on Korean language learning, we want to sort of use mathematical models of how people might be forgetting past vocabulary words and reintroduce those to make sure students learn. So we put these ideas together. We can think of taking these initial set of curriculum, all of which is defined by a set of features. We automatically generate this graph, and then we can lead people through this graph after we've specified a couple hyperparameters, which allow us to define what problem we're going to show to the student. Now, of course, this is not the only way we could choose to show items to a student. We could also just, I'll put it to the next one. We could also just use a fixed sequence of activities. We had some previous sequences of activities that were defined by an expert, which is just ways, I'll just answer in just a second, which is just a particular sequence of pedagogical activities which an expert thought would be pretty effective at helping the student learn. Peter.
When you generate the graphs, do they usually look pyramidal like this in the sense that the zone of proximal development eventually converges on a singular concept? Or do the graphs, can the zone of proximal development keep kind of expanding in all directions?
Great question. So the zone of proximal development, it depends how we go through there. I actually don't think it matters too much how much bigger it is. If it's very large, then you just have more options. And I think there's reason to believe people like variability, so that might have some benefits. Your question also does give me a nice opportunity to highlight that this is a small graph. The real graph is much bigger. So this is just an illustrative graph. And in general, you'd have a much wider graph, and so the zone of proximal development could be very big. Okay, so we wanted to think about not just how do we do adaptivity, but whether adaptivity actually matters here, particularly if we don't have a lot of data from the past. And in some of our prior research, we did not always find that adaptivity seemed to be any better than an expert progression. So we wanted to look at that here, and what did we find? Well, first of all, before we look at our results, we have to think about what better is going to mean, and this ties back to the conversation on efficacy. One of the particular challenges we have here is that we're going to do experiments online, and people can choose to leave our system whenever they want to. So it wasn't possible for us to do a standard post-test. Instead, we're just going to look at how far do they progress through the curriculum. Now, there's a number of reasons why we think how they're progressing through the curriculum is indicating true learning, and I'm happy to talk about those at the end. But the main questions we wanted to try to investigate is, do people learn faster and do they learn more? And the way that we were looking at this was essentially looking at how well they were doing on certain nodes and then giving credit to ancestors. So to giving credit to other types of items that you had to understand in order to do well. So for example, you can't get red circle right unless you understand what red is. Now, these particular criteria weren't, we considered a number of different ones and we got similar results in all cases, which is, didn't really matter. So we tried our beautiful adaptive progression. It looks at the beginning like it might be kind of promising. So this is sort of the mastery level, the level at which the student is reaching. And remember, people are dropping out at all the time. And at the beginning, it looked like, oh, great, maybe, adaptivity. So we're renormalizing here where adaptivity is 1. We're looking how much slower fixed might be. And it looked like maybe it'd be good, but actually really quickly it collapses. So why might this be? Well, when we looked at it here, it seemed like that we were doing less review early on and we were doing more review later. And the fixed approach was doing more review early and less later. And so it's likely that we were just getting an improvement of going through the curriculum faster to start with, and then we slowed down. But as we looked at this, we started to wonder whether or not review was really needed and additional practice was really needed. So in a lot of intelligent tutoring systems, we look at measuring student learning by whether or not they get things right on the first try. But in this particular tutoring system, there's very little scaffolding. So if students don't get it right correctly, they have to continue to iterate on that problem until they get it correct and they can advance. Now if you think back to sort of one of the previous ones I showed you there, let me just go back to it. Yeah, so something like this, right? There's a number of different slots that you can put these little items into, and really the possibilities are combinatorial. So in this case, it's extremely hard to guess. It's not going to be an easy thing to do well, and if by the time you finish it, it's quite likely that you've actually learned it. So we fit a different IRT model that suggested that actually people's future performance didn't really seem to depend on whether they got the last item correct initially or after lots of goes. And so maybe this repeated practice on the same items wasn't needed. And so the other hypothesis we looked at is, well, adaptivity didn't seem to help, but maybe features were too fine-grained. So if you're making everybody master everything, then it doesn't matter what sequence you're using because people have to do every single item anyway, and all you're doing is changing the order of it. So I said that there's different levels of knowledge representation here. And what we initially started with is this sort of fine grain, where we're treating every item as essentially being distinct. And another possibility is that we instead use something coarser. Now this is again just like language. When we think about teaching grammar, we don't make people show that they can do every single possible construction of grammar in order to show they've learned English. We think that after they've shown that they can successfully conjugate a verb a certain number of times, we think they might have learned the general rule. And similarly in here, when we start to think about the combinatorics, we probably don't have to check that they can do 2 red triangles and 2 green circles and 2 red squares and 2 green circles and all those different combinations in order to understand if they understand shapes, colors, and conjunctions. So we considered a coarser structure where we think about sort of number, shape, and color at this higher level of abstraction and again construct this graph automatically. And then we can create a new adaptive progression where we also have to think about, for these new nodes, which actual item to select. We call those levels here because there's just essentially different problems we're looking at. Aside from that, everything else is identical. So we again wanted to compare to fixed, and now we also tried looking at our initial fixed trajectory, but stripped out any forms of repeats. And we used a similar set of mastery. I won't go into that for time. The interesting thing here is that we actually do see with the adaptive condition that students are reaching later levels faster. Okay? So again, green is fixed. And this sort of illustrates one of the interesting challenges here is when do I care about people being faster? Do I care about them reaching 20 faster, 10 faster, 5 faster? It's hard to do these forms of analysis. And so what we did in these cases is we looked at sort of both how much faster were they and when, at different points of learning. So it seemed like people were getting to later parts of the curriculum about 1.2 to 1.4 times faster, and that's substantial. It would be very nice if we could all learn things, 1.4 times faster. So this is all small data. What we looked at here is sort of the median time to reach these different forms of different levels. So A is adaptive, F is fixed, and F is mu fixed. And you can see things like to get to level 15, adaptive is getting, students are getting there in about 97 seconds, whereas in the fixed conditions, they're getting there substantially slower. And we can see too that if we do statistical tests, that's also significant. Now, one of the interesting things here is that people were learning faster, but they did not learn more. Okay, so if you look at these dropout curves, this is percentage of the curriculum completed. They basically look identical. So no matter what condition you're in, it is not helping you learn more. You're dropping out at exactly the same, not at the same amount of time, at the same stage. So when you get to the really hard part, those really, really hard combinatorics, everybody quits. I mean, not everybody, but most people quit because it's getting really hard. But if you get there after an hour, or you get there after 2 hours, It's really the stage of curriculum that's causing people to drop out in this game, as opposed to the amount of time they've been playing. So I think this is really interesting because it suggests that from day one we might be able to do adaptivity that is significantly better even than an expert design progression, but that we have to be careful about thinking about the right level of knowledge, and also how do we actually help people persist. That this might be challenging to actually deal with that engagement problem, which ultimately will affect, especially in these open learning environments, how much they learn. Now I see that the timing is going. I'll just really briefly talk about the second issue, which is related to what Zach was talking about, is how the future of work is changing. How are we going to provide learning materials to people for all these different forms of sort of small-scale tasks in a way that's scalable? So when workers do things, they generate artifacts. They make presentations, they design products, and can we use these to train other workers? So in some ways this is a similar idea to learner sourcing, which is the idea of whatever the artifacts are that people are making when they learn, like their homeworks or their exams, those could also be used to teach other learners. Here we're thinking about worker data for learning support. So in particular, we thought about this task. This is a task that Amazon Turk workers do, and maybe other people as well, which is things like product reviews, where you might be asked to sort of review a whole bunch of different fire alarms and be able to provide benefits and cons and then write a blog post about this. So this is a sample where, from our study, where people are looking at this and trying to compare and contrast on different types of features. So the idea was, could we use prior examples that were generated by past workers, where they're just doing a task, they're not trying to teach anybody anything, and could we use these to train future workers to do this task better? So this is preliminary, this is ongoing work, but I thought there were some interesting initial results of this. One is that if you just show any example, any past sort of worker artifact to somebody, it doesn't seem to help future people work. This maybe is not totally surprising. Some of the product reviews can be really, really bad. And is that helpful to people in figuring out how to write a good review? Maybe not. Now, if we look at only high-quality reviews, we did see preliminary evidence that those might enhance the performance of people that see those before doing the task, indicating they're providing some form of training or possibly some form of anchoring, because they're providing a sort of an existence proof of what might be good. However, the most effective reviews in terms of training may be different than the highest quality reviews, which again I think is an interesting question of if we're doing this sort of sourcing of prior artifacts, that we may need to distinguish between those of them that are really getting the job done versus those of them that are going to train future workers to do better. So just to summarize, I think that there's a lot of work to be done to try and take some of these really incredible results from intelligent tutoring systems and scale them to lots of different cases where we love to provide adaptive curriculum and support. I talked about two different ones of how we can use sort of automatic structure in the materials to try to automatically sequence them, as well as leveraging artifacts from workers. And I think there's a huge number of open questions. Some of the ones that I'm really interested in is how do you create systems that are good from day one and get better over time? And I also am particularly interested in this issue of when does even the set of interventions we're looking at have any signal? So we have found challenges before where we try to optimize and make things adaptive and personalized, and we have seen no benefit. And in those cases, I would have loved to have needed much, much less student data to tell that there was going to be no benefit. So this is actually an interesting theoretical question in machine learning that I'm now partnering with some theorists on as well, of just how can you know before you can even measure the size of it if there seems to be a non-null effect. And with that, I'll conclude. Thanks.
Okay, we have about 5 minutes for questions.
Thank you. One potential response to your last question is to look how homogeneous your population is, especially, or your sample, especially when the sample is small. So we found out in testing that linear test and adaptive test will give you pretty much the same results if your population is homogeneous. But things start to look differently if you have, say, bimodal distributions in the ability with respect to which you are building the test or the learning environment. So that may be an indication that if you know that your population is heterogeneous, then the two will probably show a difference.
Yes,
So thank you.
I think heterogeneity is super important. Again, that's something we mostly can only identify once we start to have data. But I think that goes into this issue of how can we improve over time as we start to get more information about these populations.
You mentioned that you generated that knowledge graph. I don't know how to call it automatically. How have you tried exploring applying that technique to other domains that are not, like these contexts seem very visual. Like you had colors, you had shapes. To other domains that are maybe more abstract or.
Great question. We have not. I think you could certainly do that. So if it was a text-based, like if you have questions with text in them, I think you could similarly do analysis of the text and then figure out how to get an automatic decomposition.
To follow up, for the graph generation, I'm curious about one, how you're capturing the different types of knowledge that's incorporated, because let's just say that you're teaching machine learning, like linear regression to neural networks. If one node that you're recommending is talking about how a neural network works from a conceptual point of view, and then you record, they understand that concept, it's very different than being able to apply it. And then on top of that, the metacognitive skills that are involved in that. So I'm curious how you're incorporating that. And the second component to that is something that I personally find is that when it comes to curriculum design, the more explicit you're about the structure of the curriculum and how those things are connected helps a lot. And so I'm curious, when you're recommending additional components, how you're explicitly making those connections to the student.
I think those are great questions. In these cases, some of these aspects you can think of as kind of having a plug and play type approach. So things like the Q matrix method, there's lots of ways to infer this type of hierarchical structure. We picked one, but I think you do lots of other types. Another thing is that once you have data, you can start to infer whether or not things really are the same type of concept or if they should be split. And then in terms of whether or not, what is the particular type of activity to show next or how to make those connections to students, I think that's a great question. I think a lot of intelligent tutoring systems don't try to simultaneously provide a narrative as well as this sort of individual activity. You can think of this more as practice. It's not providing that overall conceptual aspect, and I think a lot of tutoring systems right now rely on expert instructors to provide that level.
What would be your ideal test setup to advance your research work? Like if you were to have a system with, I don't know, more students, specific topics, like what would be your dream system to be able to extend the work that you're doing?
That's a great question. I think I'm very interested in this retraining aspect. So I think in cases like, there's new technologies for manufacturing, things like 3D printers, et cetera. How do you reskill people really rapidly to take advantage of these new skills? So you could have a really heterogeneous set of backgrounds, but maybe pretty targeted skill sets. And so I think those would be really exciting to try to tackle. My sense is that, we have a lot of research into K through 12 and K through 16, and I'm not an expert in all of that, but I think that we're going to need a lot of reasoning about how do we take even more heterogeneous learner populations and have them very quickly upskill. So things like boot camps and student populations for that I think are super interesting.
There we go. Thank you so much for giving the talk. I thought, where you started with the authoring tools and adaptive curricula, I thought it was super interesting. And I was wondering if you could actually, the summary you did here, if you could tie it back to that, because a lot of this seems to me to be analysis of either pathways we already know how to engineer instruction for, because there are expert examples of it, or they're simple enough that there aren't that many instructional choices or complexity in how to engineer them. So how do we take this work and actually get to a mode where if I want to reskill myself for a new job and I'm looking for a brand new curriculum from day one, could you just talk about that vision, how this actually translates into that kind of day one authoring?
Day one authoring. Okay, great. You mean so no existing curriculum. So I think the last part does try to start touching on this. Like if you think of launching a new system where you want to get product reviews, this would allow you to start to do that, because as you start to get reviews and you can rate them, then you can start to use them for training. I think in general, how do we come up with curriculum that's effective and how do we break things down is a super interesting challenge. One of the things we're trying to do right now is to figure out how do you go from YouTube to tutors. I think YouTube is amazing and people use it to learn things all the time, but it doesn't provide you any feedback. It's like watching lecture videos, right? And so we're looking at how do you decompose lecture videos, sort of like activity understanding, into the subcomponents. So for example, one of my students looked at a CPR video and tried to automatically decompose it into the steps of CPR. And then once you have those, you can create these type of graphs, and then you can start to grade people in those procedures. So I think those sorts of ways of how do we take existing sort of curriculum, right, YouTube, and then break it into things in a way where you can get automatic feedback would be really exciting.
Okay, thank you so much. Thank you, Emma.